When we're talking, for instance, about spark ignition reciprocating engines, Otto cycle is, for instance, the ideal cycle for this spark ignition engine. And the first step, for instance, is you have air-fuel mixture. In this case, we're going to state that it's only air. And the first thing that will happen is that there will be a compression. And the best way to do the compression is if you have, for instance, an initial volume, which is, for instance, the bottom dead center, the maximum volume we can have, and we want to compress it to the top dead center. And the first step is to compress it, and the best way to do this compression is in an isentropic way. Then you will have, for instance, an inlet of heat due to the spark. The best way to have this inlet of heat is, for instance, at a constant volume. Then we will have, for instance, to exhaust the gases, and thus that will yield, for instance, to an expansion. The expansion is, for instance, in an isentropic way. That's the best way to do the expansion. And at the very end, we will have, for instance, a process where there will be this exhaust, and we will get rid of all the remaining heat, and there will be, for instance, an isochoric outlet of heat. So from 2 to 3, right, we have an inlet of heat, and then we have an outlet of heat, and this is from 4 to 1, and then the process starts all over again. This is Otto cycle. It is once again an isentropic compression from 1 to 2, a constant volume heat addition from 2 to 3. Then, for instance, there is an isentropic expansion from 3 to 4, and there is a constant volume heat rejection from 4 to 1, and then we start once again. It's important to analyze, for instance, the cycle and to get its efficiency. The efficiency of the Otto cycle, although it is idealized, is never going to be higher than Carnot cycle. Watch, for instance, that the volume at 2 is the same volume as 3, which is, for instance, the top dead center, and that volume at 1 equals volume at 4, which is the bottom dead center. And remember, for instance, that the compression ratio is, for instance, the bottom dead center over the top dead center. The fact that from 1 to 2 we have an isentropic compression will yield, for instance, to the fact that the temperature 1 equals the temperature 2 times B2 over B1 to the k minus 1. Or we can actually state that this is going to be equal to T2 over R to the k minus 1. The same happens, for instance, when we relate the temperature 4 with the temperature 3 in the isentropic expansion. So this is going to be, for instance, this expression would yield, for instance, to T3 R to the k minus 1. The heat that we're going to introduce is going to be equal to Cb delta T. In this case, it's going to be T3 minus T2. While the heat that we're going to, for instance, reject is going to be Cv times the T1 minus T4. Or, well, in a positive way, it's going to be, for instance, T4 minus T1, right? And remember that this is due to the situation that since we have an isochoric process, heat is going to be equal to the change in internal energy, which is Cv delta T. the only thing that remains is to get the efficiency of this cycle. And the efficiency of this cycle is usually the work that we're going to have per the amount of heat that we have to introduce. Since the work, for instance, is going to be the area, that's the area, for instance, between curves, and doing an energy balance in this situation is going to be equal to the amount of heat in minus the amount of heat out. The efficiency is going to be that divided over the amount of heat in, which yields, for instance, to 1 minus heat out over heat in. And this will yield, for instance, to an expression that is, for instance, 1 over heat out, CV, T4 minus T1 over CV times T3 minus T2, right? We can cancel CVs. Then, well, what is going to happen? We're going to have 1 minus T4, 1 minus T4 minus T1 over T3 minus T2. And then we can, for instance, input T4 in terms of T3 and T1 in terms of T2, such that we will have 1 minus T3 over Rk minus 1, that's T4, minus T2 over Rk to the minus 1, which is, for instance, T1. That's over T3 minus T2, such that we can factorize, for instance, 1 over R to the k minus 1, and we will have, for instance, T3 minus T2 over T3 minus T2. So at the very end, our expression will end up as the efficiency is going to be equal to 1 minus 1 over R to the k minus 1. Since we're using R, very important, k is 1.4, we can say, for instance, this is 1 minus 1 over R to the 0.4, or we can say, for instance, 1 minus R to the minus 0.4. That's the efficiency of the Otto cycle, and it's only depending on the compression ratio, for instance, of the volume.